When you're talking about a hybrid cement mixer, the high-voltage contactor isn't just some part you pick from a catalog. No, it's a critical safety system that you have to engineer from scratch for one of the most extreme environments you can possibly imagine. So today, we're looking at the blueprint for doing just that, a strategy dictated by, well, brutal physics and the non-negotiable laws of functional safety. All right, so let's just jump right in. Take a look at this 70-ton beast of a machine. If you had to guess, what do you think is the single most important safety device in its entire high-voltage system? Is it the battery management system? The inverter? What's your guess? Believe it or not, it's this thing. This tiny, super-powered switch. It might not look like much, but this high-voltage contactor is literally the last line of defense. It's the one component standing between everything running smoothly and a truly catastrophic failure. You could say it's the unshakable hero of this whole story. Now, to really appreciate why this little switch is such a hero, you first have to understand the absolutely brutal world it lives in. And I mean brutal. This is not your typical EV driving on a smooth highway. This is a cement mixer's gauntlet. You see, this contactor is fighting a war on two fronts, simultaneously. On one side, you've got these violent mechanical forces. We're talking constant, bone-jarring vibration and massive shocks. And on the other side, it's battling these extreme electrical loads that would literally vaporize a lesser component. Let's just focus on the mechanical shock for a second. This component has to be able to withstand 50 Gs of force. 50. To put that into perspective, that's the kind of G-force a fighter pilot might pull in an extreme, high-speed maneuver. This little contactor lives through that every single day on rough, unpaved construction sites. And you know what? The electrical stress is maybe even crazier. Imagine that giant drum filled with tons of thick, semi-solid concrete. To get that thing to start turning, the motor needs this massive breakaway torque. Well, that creates an inductive surge of 600 amps. It's like trying to move a river of sludge in an instant. And this contactor is the gate that has to handle that tidal wave of energy without even flinching. Okay, so we've got the brutal physics down, but that's not all. Piled on top of that is an absolutely unforgiving rulebook. We're talking about functional safety here, which is a non-negotiable life-or-death set of regulations that governs every single design choice you make. And all of this leads us to the highest possible safety level, ASIL D. The way you get there is actually a pretty sobering calculation. You ask 3 questions. 1. How severe is a potential failure? The answer, a fatal injury from shock or fire. 2. What's the exposure to that risk? Well, it's constant. The truck is pretty much always in a high voltage state. And 3, what's the controllability? It's 0. The driver can't do anything if the contactor fails to open. You put those 3 answers together and you land squarely at ASIL D, the most demanding safety standard in the entire automotive world. So what does meeting ASIL D actually require from an engineer? Well, it really boils down to 3 key pillars. First, you need redundancy. You have to have a backup plan, which means you need separate contactors for the positive and negative lines. Second, diagnostics. The system must know with 100% certainty if something is wrong. And third, you need huge capability margins. That just means the component has to be way, way tougher than the absolute worst-case scenario it's ever going to face. Okay, so we've set the stage, a brutal environment and these ironclad safety rules. So how in the world do you actually engineer a component to survive all that? Well, the answer starts at the most fundamental level. It starts with the hardware. That is the foundation for everything. Your first big decision is how to seal it. A standard epoxy seal just isn't going to cut it here. Not even close. It cracks under the heat, it gets brittle with vibration, and it literally gets soft at high temperatures. So the only real option is a ceramic-brazed seal. This creates a perfect hermetically sealed container that's incredibly strong, totally stable at high temps, and it'll last for more than 15 years. For this kind of job, it is absolutely mandatory. All right, next problem. When this contactor opens under a heavy load, you get a massive electrical arc, basically a little lightning bolt inside the switch. You have to put that arc out and fast. Using nitrogen gas is, like trying to put out a bonfire with a hand fan. It's just not going to work. Hydrogen gas, on the other hand, has 7 times the thermal conductivity. It actively sucks the heat out of that arc, killing it almost instantly. It's like swapping the hand fan for a fire hose. It is the only choice for breaking high-powered DC. Okay, so one of the biggest dangers when you close this contactor is that the massive inrush of current can literally weld the contacts shut. How do you stop that? With a clever little thing called a pre-charge circuit. The best way to think about it is like a small sluice gate next to a giant dam. Before you open the main floodgates, you open the small one to gently fill the riverbed downstream. That's exactly what the pre-charge circuit does. It slowly fills the system's capacitors so that when the main contactor finally closes, there's no destructive tidal wave of current. Look, you can have the toughest, most robust piece of hardware on the planet, but it's completely useless without intelligent control. The brawn is nothing without the brains. This is where the zero-error control logic comes in, making sure every single action is deliberate, it's monitored, and it's totally fail-safe. So the system doesn't just flip on, oh no. It goes through this incredibly meticulous, multi-step handshake, kind of like a pilot's pre-flight checklist. First, a system self-test. Then, and this is crucial, a weld check. It asks, hey, is the contactor already stuck shut from last time? If the answer is no, then it closes the negative side. And then it begins the pre-charge. It only closes the main positive contactor when the voltage on both sides is perfectly equal. It's a sequence designed to catch any problem before the system ever goes fully live. And this is just brilliant. How do you keep the contactor held closed without it getting super hot and wasting a ton of energy? You use something called PWM, or pulse width modulation. The best analogy is to think of it like an athlete. To close the contacts, it needs a sprinter's explosive start, so it hits the coil with 100% power for just a fraction of a second. But then, to just hold it in place, it only needs a marathoner's steady pace, so it drops the power way down. This seriously reduces heat and boosts reliability for the long haul. So, you've got a great blueprint on paper. You've built this perfect component. Are you done? Not even close, because a design is just a theory until you've tried your absolute best to break it. This is where the final proof comes in. This is where validation is king. And we're not talking about standard automotive testing here. No way. We're talking about subjecting this thing to days of intense, random vibration, hitting it with those 50G mechanical shocks, making it break a 300 amp load 10,000 times. They even do a destructive test where they hit it with a 2,000 amp short circuit. And the goal there isn't just to see if it survives, it's to make sure it fails safely without exploding. And finally, it has to survive being blasted by high-pressure water jets to prove that seal is absolutely perfect. I just want to end with this powerful quote from the engineering report because I think it perfectly summarizes everything we've just talked about. The high-voltage contactor is not a component, but the cornerstone of high-voltage safety. An error in selection or control strategy will invalidate all subsequent functional safety design. Think about that. You get this one thing wrong, either the hardware or the software, and the entire safety system of the vehicle is worthless. It absolutely has to be engineered to be unshakable.